Yeah?
Maybe a bit higher.
Okay,
Higher?
good morning, everyone.
Like this?
Yeah.
Thank you very, very much
And then
for
the
joining
clicker
us on
is right
this
there.
nice,
Okay.
warm Friday morning. Lovely to see so many
Like this?
faces here.
Okay, right.
We want to first start by thanking the Bioproducts Institute and Kelly and Cindy and Gerlene who have helped to put together these seminars. We've been really lucky to have 3 visitors here this week. And so today's presentation is going to be by Dr. Caio Otoni, coming from the Federal University of San Carlos, or UPSCar, if
Right.
you're in the know, right?
Right.
And we're delighted to have him here today. Before I introduce our speaker, I'd like to acknowledge that we're gathered today on the traditional, ancestral, and unceded territory of the Coast Salish people, including the territories of the Musqueam, Squamish, Stolo, and the last one, nations. But no, this is something that's important to us to acknowledge the land on which we are, and something that in my research group we talk about quite a lot as well, and about not just reading off the slide, but taking a second to think about where we are and to appreciate the land. And so with that, I will introduce today's speaker, who is a good friend of mine, Professor Caio Otoni, who is an assistant professor, as I mentioned, at the Federal University of San Carlos. He started in the middle of the pandemic as a professor, and fun fact, he already has permanence or tenure, so that's pretty exciting. Caio is a food engineer by training from the Federal University of Esposa, and then he did his PhD at University Federal of San Carlos, and there he was working in materials engineering, which is where he's a professor now, but also jointly with some other researchers that we know well at Embrapa Instrumentation. He then did a postdoc with Professor Watson Lowe, who we've all heard from earlier this week at the Unicamp, University of Campinas, and also joined with the National Nanotechnology Lab that's also in Campinas, LN Nano. Caio then went on to do a postdoc with Orlando Rojas. You may have heard of him. But he was doing that at Aalto University. And then we had plans for Caio to come and work with us here.
Right.
But he got his position as a professor in the meantime. And so in exchange for having Caio here, we're going to still do some of our planned collaborations. He's going to send a PhD student on exchange to join us for a year. So we're still continuing some of the plans and really looking forward to hosting his student, Juliana, later on this year. And so this has been a really busy and exhilarating and fun and tough hike week for those of you that joined us. I am very, very happy that we could have so much time with these visitors. I'm really looking forward to Caio's presentation today. And so please join me in welcoming him. And I'll leave it to you.
Thank you, Emily. Can you guys hear me back there? Yes? Thanks, Emily, for such a kind introduction. And thank you all for coming this morning. It's been a pleasure. This week has been amazing. So thanks, Emily, Orlando, Michael, and all of you who are taking good care of us. It's been really exciting. And it's my pleasure to step here and to share some things that we have been doing in Brazil related to electrostatics. I'm fortunate to have Watson making my life easier this week for introducing conservation and electrostatics in different systems, but I don't need to go from the beginning, right? So as Emily said, I am in Brazil as Watson. I've been in the States and also in Finland, and trying to connect my basic undergrad background on food science, which was related to food packaging, with materials engineering. And after that, I went for physical chemistry for a little bit, and we tried to merge everything together in Polymer Science Division of Materials Engineering Department in the University of São Carlos. It's not as famous as São Paulo, so no one have heard about it, but it's kind of a 2 hours driving from São Paulo. You're all welcome to visit and to collaborate. So as Emily mentioned, I'm there for 2 years, so some results that I'm going to show here we've done during these 2 years, but some before I got the position. So first of all, I don't think I need to introduce this to this audience, but I would like to hear from you. Do you guys have a cell phone or a computer ready there? Can you scan the QR code or just hit the link? It's menti.com/R6EIEQMA. I could have made your life easier, but yeah. I just want to know what you guys think when you hear the word plastic. Is it good? Is it bad? Is it hero? Is it villain? Let me see what we got for me. Cellulose, okay. Rubber. Microplastics, non-biodegradable, harmful, single use, pollution, everywhere, ocean. Impressive. I like this one. Fantastic, okay. Polyethylene, toxic, trash, revolutionary, wow. Permanent, waste, climate change, packaging, cheap, right? Shopping bags, strong, okay, disposable, improves life. So you can see that when it comes to plastics, there are bad and good connotations, right? It just depends on the angle, on the perspective we put on it. And it's been like this everywhere that I go discussing plastics, because plastics are really good. I mean, the synthetic, the conventional plastics, they're really impressive. They are cheap, they are strong, they are long-lasting, right? They last centuries, and this is good because you don't need to take any more resource for nature if it lasts long, right? And it's lightweight. Can you imagine flying an airplane made of glass or metals? How many fuel we would spend, right? So it's lightweight. So the main good points are it's lightweight and it's long-lasting. But that's the problem as well, because it will float and we will see it, and it lasts long, right? So the good things of plastics are also bad things. And this mismatch between the life cycle of the plastic in the application and in the life cycle is the problem, right? When we go, for instance, for packaging, I just mentioned here that packaging are materials designed for prompt disposal. This is the concept of single-use packaging. And this is not that good, right? So about 40% of plastics used in the world is for packaging, and 20% for buildings. So for buildings, it's okay, because it will stay for a while, but not for packaging. And when we go for packaging, we can see that it's polyolefins, right? Polyethylene, polypropylene, polystyrene, I mean, either expanded or not, PVC, PET. So a lot of them are non-biodegradable. So they take a while to renew in nature. They take a while to degrade in nature, but we consume them for seconds, maybe. We just open and throw away. So that mismatch is the problem. And this has been driving the concept that you put forward here very nicely of circular economy, right? So in the, I would say, obsolete linear economy, we took resources from nature, we process, we transform, we consume, and we discard. So from cradle to grave, right? When we introduce the recycling economy, then we need to keep the atom, the resources in the economic cycle, the more you can. So you just reuse, you just recycle, but it ends up in the trash still, right? And ideally in the circular economy, there is no grave. So it's from cradle to cradle. And this is the ideal case scenario, right? So we put forward the concept of extracting it from nature, transforming, consuming, reusing, and then recycling through chemically, mechanically, energetically. It just depends, right? This has been a big problem. Like they say, the tip of the iceberg, but then there is this plastic bag, right? It's everywhere. But we should pay a lot of attention because a lot of greenwashing are out there as well. This same magazine, it comes in 2 layers of plastics. You see? It says planet or plastic, and then 2 layers of plastic here. So we cannot believe in everything that we hear or we see. Yeah?
subscription and they send it in paper now.
Oh, that's great. That's an improvement. I like it. I even hide the name, you know. I didn't want to, but you know, okay, right. This one is in Portuguese because we got it there, so yeah, a couple of years ago. Right. So you put forward the concept of bioeconomy, of feeding the circular economy with bioresources, right, with biorenewables, in what we call the circular economy. And in this sense, we put forward this concept of trash to cash, right? Of upcycling whenever lasts from food processing to materials. It could be for energy, it could be for platform chemicals, but we put forward for materials, right? So we call it food waste. A lot is generated everywhere. In Brazil, it's a problem because it's not in only in consumption, but also in production, and the amounts of volume of food waste that is generated is tremendous. And we published this paper where we put forward the concept of taking monomers from food waste, or biopolymers as molecules, soluble molecules, or colloids as particles, or using just the bulk food waste without isolating the components to produce materials, right? So the routes that you can follow are several. In this case, when you take the monomer, so you can see like limonene, or you can use sugary biomass to get starch and hydrolyze it into fermentable sugars to produce PLA, or the most famous example is this green, and they call it green, right? Polyethylene from Braskem that is from sugar cane. So a lot of different hydroxymethylfurfural that you can modify and polymerize into polyamides or in polyesters, right? Different acids, different monomers that we can take from food waste and polymerize. But the concept that we like the most is extracting like biopolymers and biocolloids. So starch, pectin, some lignin, some cellulose derivatives, and also some particles. In this case, we showcase for nanocellulose. This is a paper in collaboration with the team of Orlando in Finland. And it's impressive the amount of cellulose that as a particle that we can extract from food waste. And I would like to showcase some examples that we've been doing in this way before going into the conservation stuff. But for instance, this is done by colleagues in Finland and in Brazil. I call it here the bark biorefinery because we take tannin from bark and we mix them in a mechanochemical approach to CNF during grinding, otherwise it will not stick, it will be leached out. And we produce films that are both UV shielding, that are transparent in the visible range, that are antioxidant, and that have good mechanical properties. And the same tannins we use to produce foams, right? These foams, they are self-extinguishing in terms of flame. This is real time, so I'm not speeding up the video. They really grow that fast. And they are good thermal insulators, right? So this is like an inch, the sample height. Here is 100 degrees Celsius, and here is room temperature, so that's enough to block heat transfer. This is just out in ACS Sustainable Chemistry this week. We also use what we call the fruit biorefinery. Why? Because we are showcasing with peach. So we have the fruit, and this goes to the market. I don't want it because it already has a market, right? I want everything that lasts. So that's why we call the biorefinery, because we want sort of biorefinery, right? Because we want to use the biomass as much as possible. So with this portion that lasts, then we can do different processing, different formulations to get materials with different properties. In this case, we're flexible fumes, but it could also be rigid parts. It could also be three-dimensional geometries, right? It just depends on the way you process. So depending on the formulation and the additives, the fillers and the plasticizers, we can predict the properties and pinpoint where you want to go, and then we can formulate it and deliver the properties, in this case showcased by stiffness. This is the pilot unit that we have in São Carlos. It's in Embrapa, right? So we have it's a continuous lamination machine, 2 oven drying steps, and in the middle here we have a co-lamination unit. so you can do multi-layers in this machine. And what we are doing is this solution blow spinning onto it to produce sort of a fiber sandwiched by films, which is good for some applications. We also go for the vegetable biorefineries. As you know, a lot of minimal processing takes place in vegetables, and this is what lasts, and this is what we use to produce these materials that I just showed. I'm not going into details because the topic is not this one, but just to showcase what we've been doing there. The same we do for the cuticle biorefinery, because this guy, you know, it has a lot of cellulose. It's very hydrophilic, not soluble, but hydrophilic. A lot of pectin, which is somehow soluble, but it wets quite poorly. There is a cuticle layer that has a component called cutin. Cutin is a biopolyester that hydrophobizes the surfaces of some fruits. So olive, apple, coffee beans, tomatoes, right? So we went to a pilot a processing plant in Brazil, and they generate several dozens of these trucks every day of just waste, right? So we took it from the waste, extracted cutin, and mixed with pectin, which is, as you know, is a highly hydrophilic and sometimes soluble polymer to make it water resistant and even, in some cases, less hydrophilic. Same for the seafood biorefinery. People are working with chitin. In this case, we went to, it was in the States a long time ago, we went to Alaska and got this, they have the fillet of the fish, right? And all the skin has plenty of collagen, which we denatured into gelatin and produce materials. And recently, also with Orlando and Julian Braz in Spain, and also Rosie in Vienna, we've been exploiting this chitin from insect waste as well. So insect farming, right, for protein, for food purposes. So this is just to showcase. We also been working a little bit with bacterial cellulose, and there is a company that produces this wound dressings in Brazil, but they generate a lot of scraps, and then we take CNCs from the scraps, obviously, because we want to use whatever has low value added, right, to produce composites, and the same story that you already know. The point here is that every time we need to deconstruct and reconstruct, and this is somehow a paradox, right? Why do we need to go down in size to build up again, right? So this was put by Luis from Alto. We go top down always. In this case, we go top down. We play in the assembling the materials in the colloidal state, and then we go out. We go bottom up in consolidation, right? So the key, the missing link, has been here. Then we put this chemical reviews with Orlando this year, and we shed light on the supramolecular interactions, especially when we go from sol to gel, and then we go from gel to solid, right? But this is what I want to address today. You have different forms of assembly the building blocks. So you isolate them, you assemble them the way you want to really architect the material to deliver the properties that you want at the end, right? And of course, several interactions, several forces, several bonds are at play. One of them is electrostatics, and could be hydrogen bonding, pi-pi interactions, hydrophobic interactions. I could mention several, but today I would like to focus on the electrostatics, right? I mentioned already the gel-solid consolidation, so spinning, so casting, extrusion, coagulation, regeneration, right? But let's stick to the assembly forces. So just so we are all in the same page, this might be basic to lots of you, but it's quite common in the polysaccharide and natural polyelectrolytes literature, those mixed gels where you mix a cationic entity with an ionic entity, and depending on the conditions, on the vicinity and the environment, they can complex and then create the material you wish, right? So as you know, most polysaccharides in nature, they are anionic, with a few exceptions. So what we usually do, we go in these mixed gels where you usually have a polysaccharides and a protein, right? You have to be in between the pKa of the polysaccharide and the pI of the protein, right? So we go high in pH, and then we go down in pH. We mix the species. That's the problem that Lauriane was having, right? Because when you have prompt complexation, then it doesn't get homogeneous. So you have to first get a dispersive and distributive mix, and then promote conservation, right? So that's what is usually done in polysaccharides, which are typically anionic. The opposite goes for chitosan, for instance, right? And then there are some interesting compounds like that are sort of zwitterionic because they bear both charges. They are called generically polyantholites. They are like copolymer, block copolymers. They have an ionic block, a cationic block, and in some conditions, they can complex. But what are those conditions, right? Let's take this point here, which has a high pH and a low ionic strength. So the anionic entities are going to be, I would say, active, right? And the cationic entities are going to be neutral, right? They are going to be deprotonated. So only negative forces are at play. So repulsion, no complexation, they are in solution. As we go down in pH to the other extreme, the other way around. So the cationic block is going to be active, and this creates repulsion. That doesn't promote complexation. So this is solution again. But in intermediate pH, which is what I just showed here, right? You can have both positive and negative groups active, and then you can go for precipitation. This happens with pH, but also with ionic strength. As we keep this pH and go up in ionic strength, we have what we call the extrinsic charge compensation. So the counter ions are going to be more important, and they will match the charges, and you can reach a solution again, even if you are in a pH where complexation is possible, right? I will show this behavior more clearly here. This is for sure quite typical in salting in and then salting out, when you have a lot of salt, depending on the valency as well, for sure, and attractive interactions start to dominate and precipitate again. I introduced this because I wanted to talk about celloplasticity. Professor Watts already introduced. It's so salt does to the complex what temperature does to the thermoplastics. That's why they are called celloplastics. So basically, you have a polycation and a polyanion, and this is what we call intrinsic charge compensation, when the doping level is low. In the extreme, it's 0, right? And when you put salt, let's say a monovalent salt like NaHCl or KBr, the counter ions are going to be more to play their role, and they will increase the doping level, and the complexing species are going to separate, or you're going to screen the charges, and you're not going that strong coacervation. And as you go higher in salt content, then you can really reach a solution again where the molecules are independent, sort of independent, right? So this is the picture that he showed in this presentation, in his presentation on Tuesday, where you can go all the way from a solid precipitate to a liquid-liquid phase, a coacervate, and then a solution, right? And this is what we call the salt-controlled rheology of the complex. Electrostatics can also prevent gelling, right? And this is quite common in the nanocellulose literature, because it's not that it's promoting complexation, but it's preventing complexation in the same charge entities, right? So you can go all the way from electrostatic repulsive interaction, to assembly and then attractive dominating. So you can really promote gelling by adding salt. That's because of the electrical double layer, right? And there is this classical example of they call it ionotropic gelation, where you have multivalent cations, for instance, for sodium alginate in calcium chloride, or chitosan with tripolyphosphate and different particles that you want complexation to take place instantaneously. So this is what I show here. In some cases, you want the complexation to take place. This is actually from Orlando's group, from Rafa Grande, right, and Oli Ikola as well. So 2 examples, or interfacial complexation. So you have, like in this case, tempo CNF and a polycation, which I don't recall now, but maybe different polycations, and you can really spin a fiber through electrostatic complexation instantaneous. In this case, it was chitosan, I guess, right? Same happens for alginate beads or chitosan beads, right? So you really want complexation to take place instantaneously. In some cases, you don't, because what you have is something like a curd and whey. You have phase separation in a way you don't want. So you don't have a homogeneous gel. That's what happening to Lorian, right? So then you can shift pH or ionic strength to really achieve the proper mixture, and then shift back again because it's reversible, and that's the beauty, right? I didn't point it here because it's reversible. You can go up and down, and that's what allows you to play with the system. So you can really do the same here to achieve a proper complexation. So what have we been doing with this? Let me check the time. All right. So in this case, we were working with CNF, right? And we used different chemistries, some introduced by people in this room, to make them cationic. Some, for instance, peridate chemistry or epoxide chemistry to attach some quaternary ammonium groups. And we did it for foams. It was cationic. And of course, the most straightforward application is antimicrobial, right? So complexation, it's really a complexation because this is negatively charged, this is positively charged. If they match together, there is a charge imbalance here. It will play with the barrier of the membrane. It will leak whatever is inside the cell, and it will lead to cell inactivation. But you have to really have contact because it's grafted, covalently bound. So you must have surface area in order for the entities to interact. But in the case of foams, you have to have large pores. What I want to show here is that you can have a film which will be active, will inhibit. In this case, it was E. coli as a model bacteria. But then when we go to a foam, surface area is quite large, but if the pores are small, then the bacteria cannot go inside. And you still have a higher antimicrobial effect because it's not a film, it's a foam, a three-dimensional monolith, right? But they cannot reach the inner structure. And depending on the drying protocol, you can achieve bigger pores, you can promote pore interconnectivity. Then the bacteria, which are like a couple of micrometers in size, they can really travel inside and interact in the outside and the inner microstructure, and then you can boost the antimicrobial performance. Same charge, same precursor, just different microstructure. That's what we show here, right? We have like a micro CT. It's like looking from the outside. Small pores, large pores. I hope you can see in the white arrows that you can see a lot of bacteria adsorbed, right? But then when we go for the cross section, you only see bacteria when the pores are large. And then we use the same foams, the very same foams with the cationic surface to do this multi-layer adsorption, right? So positive, negative, it's called layer by layer. It's a classical approach of building films inside charged surfaces. We did it in the cationic CNF aerogel using sodium alginate and chitosan. And it's very easy to control the charge density, as you know. And the charge density is connected to the adsorption capacity, right? So in this case, we measure through nitrogen content because only chitosan has nitrogen here. So the more nitrogen you have, the more chitosan is adsorbed. And you can really go for, like, this is going up in the number of bilayers, and this is going up in the charge density, right? And we demonstrated this as well through QCM. So you can see here that the pristine CNF, I mean, almost no charge, so almost no variation in frequency, so almost no adsorption. And when you have an intermediate, right, so going out of stoichiometry, then you can increase the shift in frequency. So it's increasing, it's not increasing frequency, right, guys, because it's negative. So it's gaining mass. And as you go for a highly surface charged, then you can have a much more variation in frequency. And I'm showing this because I really like the concept that Paula Hammond from MIT put forward. She uses like some particles, charged particles, and builds multi-layers and use this, what they call the compartmentalization approach. So they compartmentalize stuff, different stuff in between the layers, and they control the release or the responsiveness or the different activities of this particle. So in this case, it was like an antibody, an RNA, and between layers of polyarginine, hyaluronic acid, and some compounds that are common to us. Just a second. And the beauty there is that it's reversible. So you can really play with non-responsive or responsive mechanisms of triggering whatever is in the host gas as a gas in the host gas system, right? So through diffusion, through cyclodextrin inclusion complexes, but also in the responsive side. You have like swelling, and as you swell, you allow diffusion to take place faster. You can dissolve, right, one layer, for instance, if it's water soluble in acidic or in basic media. You can degrade like enzymatic and then trigger the release of something. And you can, of course, use salt to do this. And that's the beauty, right? So the same figure again, just to show that it's reversible, and you can really play with the strength of the complex based on the ionic strength and the pH. So in this case, we use partially deacetylated chitin nanofibrils and tempo oxidized cellulose nanofibrils. We produce mixed foams, right? And first of all, we did some measurements to see how was the charge depending on the pH, right? So when complexation was at pH around 7, so you can really see that chitin, which is here, bears almost a neutral charge, right? It's above the pKa, so it's deprotonated. And you have, of course, a negative charge here. So neutral with negative, no complexation. pH 6.8, right? So nothing changed, almost nothing, right? But as we go down in pH, then we have a negative, still negative species, and a positive. Chitin then now wears a positively charged group. And then we switch it to 4, and then blah, complexation takes place, right? So you can really achieve the level of mixture you want before promoting coacervation. And then you can go multi-layers, as many layers as you wish. But the beauty is that it's reversible. So we produce the foam, we dry the foam, and we wanted to decomplex the species, to get rid of the foam, right? To redisperse it. Of course, if we have something covalent, that's going to be difficult or impossible, but I call it here wet resilience because we put it in liquid medium, stirring for 24 hours, and it was gravimetric, the weight before and the weight after drying, mixing and drying, right? So if the monolith was 100% there, then the wet resilience is 100%. If everything dispersed, then it is 0%, right? So you can really see that playing with the stoichiometry between the entity that is positively charged and negatively charged, you can achieve different wet resiliences, right? So around 50-50 is the optimum. In this case, it was not the best design because we need to rely on charge and not on weight percentage, right? But what is interesting here is that when we go up in ionic strength, then the wet resilience is very much decreased because of charge screening, right? So that's another example that you can boost decomplexation or complexation in some cases. This is Carolina. This was a former PhD student of Watson Group. She was doing mayonnaise here. It's vegan mayonnaise, no egg, just cellulose stabilizing the multi-phase system. But it's also tasteless because you cannot put any salt there, right? It's really electrostatic. So she was using like IPTMAC, and she had an almond oil emulsion, which was negatively charged due to many reasons. And she was using cationic CNF, right? And the concept that they put forward is that it's acting in two mechanisms. One is sticking to the interface because of charge, right? It's negatively charged, this is positively charged. So even if it's not surface active, it can go to the interface because of attraction, right? And thickening of the continuous medium, so steric stabilization. And this is, there was a lot of debate, but they claim, they supported this claim because you can really see a decrease in interfacial tension. This is almond oil, this is CNF dispersion, and this is the test that you see that is quite common to you. And you can really play, as I told you, with the stoichiometry of the reacting species and the surface charge density. So you can really tune this as well. So what she did, she tested a lower degree of substitution, 0.14 millimole per gram charge, cationic charge on CNF, 0.5, which is a bit higher, and she used the tempo CNF as a control to compare, right? And what she got is that this is familiar to some of you. This is a lumicizer. It gives you a number in the end. So the higher the number, close to 1, it's more unstable, and closer to 0 is more stable. Of course, kinetically, right? Not thermodynamically. So what she saw was that tempo CNF was much less stable. And it's still, the cationic one is still sitting in the bench, and the other one was like less than 1 day stability, right? So this is microscopic stability. And through cryo-TEM, they could see, or they could guess and propose that CNF was sticking to the interface, so adsorption onto the interface because of charge mismatch, and also forming a network and increasing viscosity and preventing coalescence in the continuous phase. So that's another application of electrostatics. And the last example that I would like to give is this, what we call cubosomes. Some of you may have heard about it, but it's a lyotropic liquid crystal. In this case, it is made of phytantriol and pluronic. So we will self-assemble, and pluronic, I mean, the cubic phase is pretty interesting because it's bicontinuous. So you really have a hydrophobic channel here, a hydrophilic channel inside and also outside. So it's bicontinuous, and it's good for carrying both hydrophobic and hydrophilic compounds, like drugs, like whatever you want, right? And whatever fits here. And you can make a dispersion, a kinetical dispersion of cubosomes in water. You can top-down break the particles, and you can reach like hundreds of nanometers in size, and stabilized by pluronic F127. So this is a cryo-TEM really showing the structure. And it is negatively charged, naturally, right? So this is what we have been doing. We have this BC membrane. I have a disclaimer here. BC does not stand for British Columbia, but for bacterial cellulose, right? So we had this membrane, BC membrane. We had a cubosome dispersion. We freeze-dried this membrane, so it's porous, and we allow it to reswell in cubosome dispersion. And then this is confocal microscopy. It had NIORAD, so a fluorescence dye, which is hydrophobic. And you can really see that the cubosomes are spread evenly, homogeneously everywhere, right? So we cannot resolve the size of a cubosome because of the threshold of the technique, but we can see how it is dispersed. And we did it in situ as well. So we had a cubosome dispersion, we had the BC producing culture medium with the bacterium, and the membrane was already synthesized extruded by bacteria containing cubosomes. And you can see that there is a less evenly dispersion, but still okay. But the point here is that you have a membrane and you have a cubosome, a big membrane with a tiny small cubosome, and this is the amount of phytantriol outside the membrane. So we are tracking here the leach of the cubosome from the membrane to any release medium. And it's quite high because you can see that more than 50 after 7 days. It's promising for the beginning, but after 7 days you have a high leaching of the cubosome, which might be good, sometimes not. So what Denise, which is a postdoc in the group of Watson, did, she was like, it's like trying to have soup with fork. You simply cannot because it's a big mesh and a tiny small particle. So it will not retain there. It will not be stuck there, right? So what she did, she played with charge, and that's why I'm saying this, because she added a cationic surfactant. And I told you, the previous one was anionic, and this one is cationic. And she used hyaluronic acid, which is, as you know, an ionic polyelectrolyte, right? But she did something else. She cross-linked. So she used pyridate chemistry to open here the ring, create 2 carbonyls, and then added ADH. So this is a very fast cross-linking reaction. And this was enough to retain the cubosomes there. So this is the confocal for this system, for the hyaluronic acid. You can see that in this case, the degree of cross-linking, low, intermediate, high, did not change the cubic structure of the cubosome, nor the structure of the gel, except for the time that it disintegrated and allowed the cubosome to leach. So with low degree of cross-linking, after 24 hours, all cubosomes were gone, right? As she went high in the cross-linking degree, then after 7 days or something, it reached total. And high degree of cross-linking, then it was still there. So this is really a way of playing with inner microstructure to allow the cubosomes to migrate, to leach or not. So you basically have several mechanisms that you can play with, right? So a drug, in this case, was sodium diclofenac as a model drug, but it could be a hydrophobic, a hydrophilic, a dye, right? So it's in the membrane, in the wet environment. So it will be released promptly from the membrane and from the cubosome, right? You also have some leaching of the cubosome to the release medium, which could be the blood, or could be anywhere, right? And there is the gel disintegration, the matrix that is sticking things there, like the spoon, that can also be lost, disintegrated, and then allow the full release of the cubosome. So different time scales that can really prolong the release of whatever you want to be there. So just to finish, we did this also with Orlando in Finland. We started, now Felipe is back in Brazil, but he was doing in situ cubosomes and BC as well. So he was basically doing this liquid marbles. So he had a droplet of culture medium. He was coating it with PTFE, with Teflon particles, to allow oxygen access, right? And inside this culture medium, he was putting his cubosome dispersion, already dyed, with NioRed, the hydrophobic part, and with fluorescein, the hydrophilic part, right? So he allowed the fermentation to take place, as you know, purification, and at the end, what he had, right? This is just the cubosome dispersion, undyed, fluorescein, NioRed, and this is both fluorescein and NioRed. So he did this, what we call biofabrication, and he had this now no membrane but capsules, right, in different medium. So you can really see that it has fluorescence, and this is NioRed, and this is both. And the beauty here is that you can really play with the release kinetics, right? So in this case, again, fluorescein in water ethanol mixture, NioRed in water ethanol mixture, and this is both, right? So releasing yellow fluorescein and red NioRed. With that, I hope I convinced you that charge does matter, right? And I showed just a few examples, but the potential for conservation is huge. Professor Watson already mentioned several, starting from membranous organelles to reactors in confined environments, to barrier layers, to encapsulation and slow release or controlled release, to controlled rheology, gels or solids, right? And all of these we claim to be quite scalable and friendly because we don't need harsh chemicals and etc. Just to emphasize what Professor Watts already said, we have 8 fresh openings to be filled soon. Some of them are related to cellulose and to biorenewables and to polyelectrolytes. So 3 PhD positions in polyelectrolyte complexes and responsive nanocelluloses, and also 5 postdoc positions, one of them in cellulose vitrimers in this what we call the colloids Brazil cluster, in which Emily and Rolando take part, and it's coordinated by Watson. So thank you very much to all of you for your attention, for those of you who are nicely hosting us, also to the mentors. In Brazil, we are running a group called Materials, so materials inspired by trees. So feel free to engage, and thank you.